So question 1 opens simply with a request to give the Kp for this expression. So easy question, but just be careful. First of all, make sure it's Kp, not Kc, so no concentrations. That means no square brackets, otherwise it's confusing. And just check that it's a simple homogeneous equilibrium, so you can see all of the state symbols are gaseous, so it's just a mixture of gases, so there's nothing that needs to be left out, as there would be for a heterogeneous equilibrium. Sometimes when you see water in an equation, you always have to be careful, because if the other reagents were in aqueous solution, so if the state symbol was AQ, then that's when the water gets left out, because it's a solvent and it's in huge concentration, so you treat it as constant. But that's not the case here. These are all mixtures in a gas, so everything goes into the Kp expression, so we just get Kp equals, and then the stuff on the right, so we've got the partial pressure of HNO3, and that's squared because there's two of them, times the partial pressure of NO, and then everything on the left goes on the bottom, so the partial pressure of NO2, and that will be cubed because there are three of them, times the partial pressure of the steam. And that's the first one. Now part B is asking us to calculate the value of Kp from some experimental data. And this kind of question where it says, right, first we make a mixture at the beginning which isn't at equilibrium, and then we leave it for a bit and it comes to equilibrium and the concentrations change. That's a really common, really important kind of question that you have to be absolutely confident you know how to do. And the way to do it is to write down the equation again and make that the heading line for a table. And if you do this just as a sort of instinctive way to address these questions, it's going to save you a lot of trouble. So the idea is that we're going to write down, first of all, the initial moles. In other words, the moles at the beginning, before it's come to equilibrium. And it's very important that you remember that these are not equilibrium moles, so you're not going to be able to use these numbers in actually calculating the equilibrium constant, but you need to know them to work out what the equilibrium concentrations are. So it told us that we had 1.500 moles of that and 1 mole of steam. It doesn't mention having any of those in the mixture at the beginning, and that means there wasn't any, so we can put 0 down for these. So that's what we had at the start, and then it says it was allowed to come to equilibrium, and that at that point the amount of NO2 had decreased to 0.300 moles. So we put in our second line, which is equilibrium moles, and this has gone to 0.300 moles. Now you have to be very careful with your prepositions here. It said it had decreased to 0.3, not by 0.3. It's a very easy mistake to make, to think, oh yeah, the decrease was 0.3, but that's not what it says. So you have to read the question carefully. So what you then do is you focus on the change. And you say, right, that went down from 1.5 to 0.3, so that's a decrease of 1.2 moles. Now, the equation relates the number of moles of everything involved in the reaction. So it tells you, for example, that 3 times as many moles of NO2 react as of H2O react. And we know that the moles of NO2 that reacted was that 1.2, because that's the amount the moles decreased by. So this will decrease as well, but only by 1/3 as much, because of the 3 in the equation. So that goes down by 0.4 moles, which gives us 0.6 moles of that. In the same way, everything on the right, if this stuff is being used up, so the amounts are decreasing, the stuff on the right, of course, is increasing, because that's what it's being converted into. And again, the numbers in the equation tell us by how much. So that too tells us that the increase in HNO3 is twice as big as the decrease in H2O. Okay, because 1 H2O goes to 2 HNO3. So that will go up not just by 0.4, but by 2 times 0.4, which is 0.8. Okay, so that will give us our moles of HNO3 at equilibrium. And finally the NO, well, you can see you get 1 NO from 1 H2O, so the change is going to be the same, but just in the opposite direction. We lose 0.4 of water, so we gain 0.4 of NO. which gives us 0.400 there. Okay, so now we know the moles at equilibrium. And that would have been the same approach regardless of whether it's Kp or Kc. But what happens next is, because it's Kp, you remember that you have two more steps. You need to convert those moles into mole fractions, and then you need to convert the mole fractions into partial pressure. So the next line is mole fraction. And to get that, you add up the total of all of the moles in the equilibrium mixture. So we've got 0.3 plus 0.6 is 0.9, plus 0.8 is 1.7, plus 0.4 is 2.1 moles. So the mole fraction is just these numbers of moles divided by 2.10. So if we compute those, we get 0.143 for this one, 0.286 for that one, 0.381 and 0.190. And you can do a quick check, which may be worth doing if you tend to make mistakes with numbers, because those should add up to 1. Because obviously if we're dividing the total number of moles into fractions, the sum of those fractions should add up to 1. And you can see just by sort of looking roughly at what those are going to add up to that looks right. So that may be a check that's worth doing. To turn those into partial pressures, which is what comes next, we're going to multiply by the total pressure. And it tells us in the question that the total pressure is 900 kilopascals. So we're just going to multiply these numbers by 900, and it's going to give us partial pressures in units of kilopascals. So if we do that, we get 129 for this one, and 257 for that one, 343 and 171. So now we have all the data we need, and we can just feed them into the Kp expression that we've already written down. Okay, so that's our Kp expression. So we just take the numbers we've just worked out and put them into there. So we get 343 squared for the HNO3 times 171 divided by 129 cubed. Don't forget these powers when you actually do the calculation. That's an easy mistake to make. Even when you've written them down, just double check on your calculator that you did remember to square that number and cube that number. And if you've worked that out correctly, you should get 0.0365. And then you have to worry about the unit. And it's really important that you just memorize these recipes for getting the units of Kc and the units of Kp. So in either case, remember the quick way to do it is to just add up the powers on the top line. So we've got 2 plus 1 is 3, and then subtract the powers on the bottom line. So we've got 3 minus, bottom line adds up to 4, so 3 minus 4 is minus 1. And that means the units will be kilopascals, because that was the pressure unit that we were using. It could be pascals, it could be atmospheres, but in this case it was kilopascals to the power minus 1, because it's 3 minus 4, and that gives you the unit. Part C gives us a bit more information, which is that when the temperature decreases, the amount of NO2 in the mixture also decreases. So the partial pressure of NO2 goes down. And it's almost worth writing those down, just scribbling them down so that you keep those in mind and make sure you get it the right way round. Very easy mistake to make is to forget it's talked about a decrease, because you may have mainly, in previous examples you've done, you may have talked about temperature increases. So you've got to make sure you get it the right way round. So perhaps just scribble that down. And again, make sure you answer both bits of the question, because it asks you two things from that. One is what happens to the value of Kp, and the other is what can you learn about delta H for the reaction. And again, maybe it's worth writing those down, just quickly scribbling them so that you remember, yes, I've answered that, yes, I've answered that, and don't just do part of the question. So let's talk about Kp first. So the key thing is that NO2 comes on the bottom of the Kp expression. So if the amount of NO2 has decreased, the partial pressure of NO2 will therefore have decreased, and the bottom line will have become smaller. So what we can say is that when the temperature decreases, the bottom line becomes smaller. And obviously that's happened because the equilibrium has shifted. When the temperature changes, the equilibrium changes. So if there's less of this, there's more of that, because the equilibrium's just shifted to the right. And that means that the top line is bigger. And we know what that means. That if the top line's got bigger, the bottom line is smaller. So that means that the value of Kp has increased. And again, it's a really good idea to write down a statement like that about what happens to the top line and the bottom line. Because first of all, you're much more likely to get it the right way round if you write it down. And secondly, because it shows the person marking it that you haven't guessed, that you've actually worked it out by thinking about the top line and the bottom line. Turning to delta H then, we now have to use Le Chatelier's principle to figure out what went on here. With temperature changes, as far as A-level is concerned, that's the only way to figure out how the equilibrium is going to respond. So we already know that it shifted to the right because the amount of NO2 decreased and the Kp got bigger. So we've got that when the temperature decreases, we know that the equilibrium shifts to the right. What Le Chatelier tells us is that when you increase the temperature, the equilibrium will shift in the direction that opposes the change. And the way you oppose a decrease in temperature is to try to raise it up again by giving out heat. And that means you're going to shift in the exothermic direction. So you should write that down. And I think you should write down a proper Le Chatelier type sentence to explain that. Don't just say, when temperature decreases, it goes in the exothermic direction. What you should say, I think, is that the equilibrium shifts in the exothermic direction to oppose the change. And if you just put in that little clause, to oppose the change, that makes it clear that you've thought about it and you haven't just memorised that temperature decrease shifts it in the exothermic direction, but that you've related that to Le Chatelier's principle. And then you just bring those two ideas together. It goes to the right, it goes in the exothermic direction, and that means that it's exothermic going to the right. In other words, exothermic in the forward direction, which is to the right. And if it's exothermic in the forward direction, that lets you answer the question, which is that delta H is negative. Because the sign you give is the sign for the forward reaction. If you stopped at that point and just said it's exothermic in the forward direction, you might get the mark, but the question actually said, what about the sign of delta H? So probably it wants an explicit answer like that. Delta H is negative.